Good evening, my dear JEE warriors. Time for the third class and the last class of rigid body and rotational motion of your class 11th NCERT syllabus. But today, we're going to take it up to obviously JEE level and starting right from the basics, we are going to start with angular momentum. Then, how is it related to rotational energy? Then, we'll try to find the angular momentum of point masses and rigid big bodies which are either rotating or rolling. Then we will take up relation of angular momentum with torque, and then finally we will see the conservation of angular momentum. So these are the subtopics or articles that we are going to cover in this session. All right. Hi Rehan. Hi Bhumika. Welcome Jatin. Welcome Abhijit. Yes, long time. This class got shifted and I was also, unable to take it due to, personal reasons, and I had to travel and I didn't have access to my studio. So finally I'm here and let's complete this chapter because I wanted to do this chapter for all of you because this is very critical chapter and I don't want to do it in 1 hour or 2 hours. That's why I split it up into multiple parts and I'm taking up a detailed class for every single topic. We had separate class for moment of inertia. We had separate class for torque and pulleys and rolling part. Now this is a separate lecture for angular momentum and its conservation. Okay, if you have not yet marked your attendance, please mark it by liking the video and say hello, say hi to your new friends in the chats, or if you are watching it recorded, please say hello in the comments. All right, I'll be reading your comments even after 1 year, 2 years also. I keep seeing your comments and that makes me really, really happy. All right, thank you so much, guys. It's time to begin. And do not forget the entire lecture PDF will be available in the description. You can even ask doubts of this lecture to Ved AI. You can also create smart quizzes and smart notes apart from the handwritten notes that I'm going to give you of today's class. Yeah, all you need to do is just make sure that you are using this particular link. Ask with any doubts, click on that particular link, and right now the lecture is going on, but after the lecture is over, you will see Ved will be able to help you with your doubts of this lecture and also create quizzes, create problems for you, questions for you, and also Ved will help you give the timestamps of this lecture when what was done. So all of it, Ved is also listening alongside you. Okay. So use these features. You will see it somewhere over here. Right now, I don't know, for some reason it is not showing for me because I have some filters and all of that are on. But yeah, you will have to sign up. It is absolutely free. You don't have to pay anything for Ved. It's absolutely free. You just have to use your Vedantu account once a page will come up for logging in. Okay. Hi, LS, Ronnie, welcome aboard. Sir, will you play do fluids and solids? I will do Bhumika, fluids and solids, maybe later on after December, not now, because I might have to, take up more classes of class 12 and JEE 2026, but I will definitely try and take fluids and solids also very soon. Before your 11th gets over, I'll definitely try and do it. Okay, cool. So let's begin with the class and let's start with the concept of what is angular momentum. Now see, if you have a body of certain mass which is in motion, which is in motion, then we say that such a body which is in motion has something called as linear momentum. Linear momentum. You are doing something, let's say you're studying, you keep studying every day, you build that momentum, right? You are, as a subject, as an object, doing something, activity builds a momentum. Same way, this mass as a body doing this action of motion builds linear momentum. This is basically the concept in translational motion. This is in translation motion. This is now translation. But a similar ideology exists in rotational motion. In rotational motion. And that will no longer be called just momentum or linear momentum. You might have guessed what it should be called. Just like force is called moment of force or torque. Here in translation, it was inertia. In rotation, it is called moment of inertia. So if this is linear momentum or just momentum, here it will be called the moment of momentum or angular momentum. That is the word for it. But what does that body do exactly? So the body which is there, either it is maybe a particle, a point mass, and maybe it is just going around a circular path like this, or maybe it is some kind of a rigid body and there is some kind of an axis over here and this body is rotating. So this object, this body which has some mass, some moment of inertia is now rotating. So that possesses nothing but angular momentum. Angular momentum. Sometimes it is also called, sometimes it is also called moment of momentum. Moment of linear momentum. Moment of linear momentum. The moment you get, oh my god, too many moments out here. What a cute moment. Okay. So guys, the moment you have this word called as moment of something, it means you are converting it into rotation. You are finding that analogy in rotation, like moment of force is the force equivalent in rotation. Moment of inertia, the equivalent of inertia in rotation. Moment of linear momentum, the equivalent of linear momentum in angular momentum. That is what it means. Is this concept clear? To give you examples of linear momentum versus angular momentum. You are fighting with your friend. Your friend takes, you should not fight with your friends. Okay, you're fighting with some random dude. You are taking this hand like this, wrist like this, and you take it behind and you punch like this. Shreyas sir punching, guys, to the kids, first time on YouTube, public. Wow, okay, so you can maybe make memes out of it. All right, so Shreyas sir takes his hand back and just like this. This is linear momentum. But Shreyas sir takes his hand like this and hits like this. That is angular momentum. So me doing this is linear momentum. Me taking my hand like this and rotating top, it will hit on somebody's face like this. This is angular momentum. A mass rotating, a body rotating, angular momentum. This is linear momentum. Is this clear? The difference between the two? All right. Is this absolutely clear? Let me know quickly in the chat box, my dear students. Let me know quickly in the chat box, my dear warriors. Yes or no? Clear example? Yes, sir. I understood. Please don't punch me anymore. Please don't slap me anymore. All right. Perfect. Great. So, what is the formula of this? It should be just like torque, where one extra position vector, radius vector comes about the axis of that main linear quantity to convert it into angular quantity. So, for that, say for example, we have this particular axis, we have this particular axis, and I notice that I have a mass, I have some mass over here, and let's say that particular mass is going like this with some velocity, all right, that is some mass, and that mass is right now at some distance, perpendicular distance from this particular axis, maybe like this. So this is very important. This is perpendicular, okay. But these two may not be perpendicular, that is okay. And that is the position vector of that particular mass. This is the position vector of that mass, which has some velocity. And there is right now, like I said, some angle between them, some angle between these velocities and position vectors. Let's say I call it theta. Let's say I call it theta. Then the angular momentum, because this mass is going behind this axis, coming from this side, going in front and going like that. If you visualize the path, kind of, it looks like this. So if you take the fingers of your right hand and curl it about this axis, you notice the thumb is going up. So that's exactly where your angular momentum is. that's exactly where your angular momentum is going to be. So the angular momentum will be a vector which is going to be like this. This is your angular momentum vector using your right hand thumb rule. Visualize this, guys. This is very, very important. Please understand our R and velocity are in one plane. R and velocity are in basically one plane over here. This is very, very important. R and velocity are in one plane. Angular momentum is perpendicular to that plane along that particular axis given by the right hand thumb rule. Yeah. All right. Abhijit, full syllabus almost by next year start. Yeah. Oh, don't worry, Abhijit, it will not be discontinued. Hi, uh, Pumima. Abhijit, I'm not avoiding you, man. I'm focused on this lecture. Okay, Rima, thank you so much. Good evening, Evening Star. Nice to see you guys back over here. Okay, so this particular angular momentum, magnitude wise, depends on R, M, V, and sine theta. So it is basically R multiplied by mass into velocity multiplied by sine of theta. This is the magnitude part of it. But since you see sine theta, since you see two vectors multiplied to give a third vector, it has to be a cross product. So the angular momentum vector is given by the vector r, which is the position vector of that mass, cross producted with mv vector, which is the same as saying r vector cross the linear momentum vector. It's one and the same thing, guys. Yeah. M into V is linear momentum. Sometimes people write M before also. That's okay. The order does not matter. But yeah, R should be before V. Do not put V cross R because then the direction will be completely opposite. Mass is a scalar quantity. Scalar quantity you can put wherever you want. It doesn't matter. Okay. But R cross V or R cross V, that is the exact formula. So it's time that we block this. So this is the formula for angular momentum vector quantity. This is the magnitude part of it. So this is nothing but your magnitude. This is nothing but your magnitude. This is nothing but in vector form. In vector form. If you ask me what is the SI unit, what is the dimension and all of that, it's not that big a deal. See guys, this is meter, this is kg meter per second. So kg meter per second is the unit of momentum. Correct? Multiplied by meter will be kg meter square per second. So the unit, SI unit will be kg, and then you have meter square per second. That's one thing. If you ask me what is the dimension, of angular momentum, kg means mass, so m raised to 1, meter means length but raised to 2, second means time, so raised to -1. This is a vector quantity. This is a vector quantity given by the right hand thumb rule. Right hand thumb rule, where you first point your four fingers of your right hand in the direction of r vector, slowly bend it towards, curl it. Slowly you are going to bend those fingers, curl it towards, the velocity vector, or basically the momentum vector. Then the thumb will, then the thumb will, then the thumb will point in the direction, then the thumb will point in the direction of the angular momentum. Simple cross product rule. So take the four fingers of your right hand in the direction of r, slowly bend it towards the velocity. The thumb always points to the direction of angular momentum. This is how you define angular momentum for a point mass. Very, very important. It's a point mass, not a big body like a disc or a cylinder. Is this absolutely clear? Okay, so I hope you got your answer, Abhijit. Yes, good evening. Everybody clear till this point? Everybody clear? Absolutely. Okay, cool. Now, sir, Are there some techniques by which we can find angular momentum in easier way? The answer is yes. Just like for torque and everything, there are easy ways for finding angular momentum, and I will show that to you. Say for example, okay, this is your this is your velocity. This is your velocity, and let's say from the top view, this is basically your axis, and let's say this is your position vector. Let's say this is your position vector. This is your velocity vector. You can also call it momentum vector, one and the same thing. Now, usually what we say, angular momentum, fine, you can just say it is the cross product of your position vector cross our linear momentum vector. That will give me the angular momentum vector. This is the vector way of getting it. But there are easier ways if it is not in vector form, or you can find it out in some convenient way. What are those two tricks? Number one, observe this carefully, where you take the position vector as it is. You take the position vector as it is, but this momentum vector, right? This momentum vector, split it up into two parts. Split up that momentum vector, which is right, into two parts. One is perpendicular, one is along that position vector. One is along that position vector. So it looks something like this. So this was your original momentum vector. This is theta. So this is P sine theta. This P sine theta means it is perpendicular. This is parallel component. Ignore that. This is P parallel, which is P cos theta. Okay. Why is it parallel? Because it is parallel to the position vector. Our axis is still over here. This is still our axis. Then we can just write the magnitude of the angular momentum as observe this carefully, very, very important. This is r multiplied by P sine theta, P sine theta. But what is P sine theta? It is nothing but the perpendicular component of the momentum. It is nothing but the perpendicular component of the momentum. What I had written down over here, Rp sine theta. So mv is nothing but momentum. So Rp sine theta, P sine theta is perpendicular component of the momentum. So this is one convenient way where you have momentum, you take out only the perpendicular part. The other parallel part has to be ignored. So this is the part which you will use, and this is the parallel part which you will ignore. This is one way of doing it. This was also done in force, torque. Force was at an angle, at some position. You take the perpendicular force, R cross or R into F perpendicular gives me torque. The parallel force never gives torque. Do you remember this, guys? How many of you remember this? Now, the another thing that you can do is okay, you have the momentum, over here. Instead of splitting the momentum, you split the position vector. But for that, you will have to extend that. Line of momentum like this. This is your line of momentum, guys. This is your line of momentum. This is your line of momentum, and this is still your axis. This is still your R. This is still your velocity, or you can say momentum. Now, instead of splitting momentum, you split R and you take only the perpendicular distance on that line of momentum. Perpendicular distance on that line of momentum. This will be basically theta. This will be R sine of theta. R sine theta means it is R perpendicular, the perpendicular drawn on the line of velocity. And that is exactly what your angular momentum will be now. Instead of putting sine theta with momentum, I am going to put that sine theta with R. I'm going to just shift it mathematically. It makes no difference. Rp sine theta or R sine theta into P is one and the same thing. So now what you will see is that the angular momentum is perpendicular r multiplied by p, is perpendicular r multiplied by p. So both ways you get the same output or result. It's just a matter of convenience or choice. R into the perpendicular P, or you take the perpendicular R on the line of P into the momentum itself. Both will give me the same answer. Yeah. Does this ring a bell? It was something like this only in torque also. In the previous slide, why did you take the angle like that? Okay, very good question. Chapter of vectors, whenever you have two vector quantities, the angles have to be measured when they are arranged tail to tail. This is correct. But if it is like this, don't take this angle. Then you'll have to slide this vector. You have to slide this vector so that their tails are joined together. Same thing if you see over here, my dear students. Same thing if you see over here, my dear students. This vector R and vector V's tail and head are joined. So you cannot measure. You cannot measure. Oh, sorry. This as the angle. I'm so sorry. I put this as the angle. That is bad. It should have been this R vector has to be slided here, and this will be theta. That will be theta. Thank you for pointing it out. By mistake, I had put my theta over there. Oops. Why is this like that? Okay. This is not the right angle. This is not the right angle. The correct angle that you should be measuring is basically this one. So I'll mark it over here right now. This is theta. Yeah, this is the correct angle. Okay, perfect. I think now it is fine. R and V vector. Okay, because over here also we have done the same thing. R and momentum vector, we have taken this as the theta. Yeah, I just corrected it. Thank you for pointing it out. Yeah. All right. Good evening. Sai Vignesh, clear Rehan. Okay, clear Abhijit, clear evening star Rima, Purnima, sorry, Pumima, Bhumika, everyone, LS. All right, Jethra, Rio. Great. Perfecto. Shall we go ahead? Hey. No, I've not forgotten my neat Pandus and Champas. I'm still teaching in the DNA batch, the DNA crash batch, along with the J Sigma batch, the crash batch. And also, I have requested all my Pandus and Champas from NEET. Please feel free to join the JEE English channel and continue watching my physics classes here. Okay. Yeah, it is of J level, but still it will be useful only. Doing more is better than doing less. Okay. Great. Moving ahead, let's do some questions based out of this. Now, see, imagine I will give you 3-4 scenarios and you have to tell me in which cases is there angular momentum and in which direction it is. And you have to also figure out if the angular momentum is zero in any of these particular cases. All the white dots are the axes. So first case, the momentum is like this. Next 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 case, the momentum is like this. And next case, the momentum is like this. Okay, these are all different cases. You need to figure out which direction, if at all, angular momentum is in all these cases. Case 1, case 2, case 3, case 4, case 5, case 6. Okay, the first thing that we should do in all these scenarios is figure out where our position vector is. This is our position vector. 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 That orange dotted line are our position vectors. Now it becomes easy to figure out. In this case, R vector and P vector both are parallel to each other. Can you see it? R vector and P vector are parallel. So if they are parallel, what is the angle? 0. And sine of 0 is how much? 0. So the angular momentum is not there. And whenever momentum will pass through the axis, what will happen? Momentum passes through the axis, guys. then think this momentum, if it passes, the line of momentum passes through the axis, then the perpendicular distance will vanish. So if this becomes zero, the angular momentum will also be zero. And that is the reason why in this case, angular momentum is absolutely zero. In the second scenario, the r vector is like this, momentum vector is like this, angle is 180, sine 180 is also zero. Not just that, whenever the perpendicular distance on the line of momentum, if you draw perpendicular, it will be zero distance, it will be zero. So angular momentum is absolutely zero. Yeah. Now, in this scenario, you can see the momentum is going like this. Just take the momentum vector, rotate it about the axis. 100% angular momentum is there. So, definitely angular momentum is there and it is clockwise. In this scenario, take the momentum and see how it rotates. Definitely angular momentum is there clockwise. In this scenario, take the momentum about the axis and you can see it is definitely there. Angular momentum is existing in this case also clockwise. In this case, take the momentum around that axis, it is anti-clockwise in the last case. So case 3, 4, 5 and 6, angular momentum is there. But in the first and the second scenarios, it was passing through the axis. In all such cases, the perpendicular distance is zero. So there is no absolutely angular momentum available. Okay. I hope this is clear. Why is the position vector always meets at the tail? Uh, Position vector always has to locate a particle. So it starts with respect to the origin or the axis and it locates the particle. That's why the position vector will always end up at the mass or at the point where the force is applied. It has to locate something. So it will be directed towards it. It will be directed towards it. Okay. All right. Hi, Manoff. All right. Is this absolutely clear? Okay. Let's do next question coming up on your screen. And here it is. A particle of certain mass is projected with some velocity, making an angle of 30 degrees with the horizontal. Making an angle of 30 degrees with the horizontal. The magnitude of the angular momentum of the projectile about the point of projection when the particle is at the maximum height is how much? Okay, let's draw the scenario. This is a very common model of question, but we will see it properly of how to do it. So our first thing is velocity will be like that initially, but after reaching the topmost point, it will be like this. So originally, if the speed was u, making angle theta, after it reaches the top and before it starts coming down, you will see the velocity will be u cos theta at the topmost point. That is the first thing that you should realize. It will not be same. Remember, projectile motion, horizontal component remains constant, vertical component keeps on reducing, becomes zero. So the only component which remains at the topmost point is u cos theta. Okay. Next thing, when it is at the maximum point and you have to measure it about the point of projection. That means my axis which is considered is this as the axis. So this is the point about which I have to measure the angular momentum of this guy. Now the mass of that guy at this point, let's say, is m. Position vector, guys. Position vector will be this. This is technically my position vector. This is basically my position vector. Now, the problem is if you try to find angular momentum using the standard formula, r into m into velocity into angle between them, trust me, this angle will take a lot of your time to be found. This is the actual angle between the position vector and the velocity vector. And mind it, it is not theta because theta is the larger angle here and this angle is way different. This angle is way different than theta. So it is, the theta is not the same theta of the projection. How many of you understood this concept? Finding this theta will take some time. Okay, you have to use trigonometry, you have to find height, you have to find the base and all of that. But yeah, it is time consuming. How many of you got that point? All right. Okay, perfect. Now, what can we do? I will think of the two techniques which we have just learned. Either split momentum or split position vector. Which one do you think is more convenient, this or this? Splitting the moment or splitting the position vector? One of these techniques is going to definitely help me. So if you notice, if I have to split momentum vector, again I have to know this angle which I do not know. I think splitting R will be better. I'll tell you why. This will be the line of momentum. Can you see that? This is basically your line of momentum. And on that line of momentum, I can conveniently draw perpendicular R. I can conveniently draw a R perpendicular. Oh, my job is done. So now I can just say my angular momentum is nothing but R perpendicular multiplied by the momentum itself. R perpendicular multiplied by the momentum itself. And this is easy to find because this will be the maximum height. This will be the maximum height of a projectile motion, which is u square sine square theta divided by 2 times of g. So instead of r perpendicular, I'm just going to put u square sine square theta divided by 2g. This is the first thing over here. What about the momentum? Momentum is m into velocity. Mass is mass, velocity is u cos theta. So solving it further, I will get angular momentum is m is there as it is. U into u square is u cube. We will have sine square theta multiplied by cos theta, the whole thing divided by 2g. But I think they have given theta over here as 30 degrees. So if I start substituting that, I will get mu cube. Sine 30 is half. So half square. So half square. Cos 30 is root 3 by 2. So put root 3 by 2 over there. The whole thing divided by 2g. So what is this going to be? Root 3 will be there on the top. Mass will be there on the top. U cube will be there on the top. And at the bottom, 2 square is 4 into 2 is 8 into 2 is 16 and g is also there. So 16 times of g. Is that right, everyone? So root 3 mv cube divided by 16g, which is our D option. How many of you understood this concept clearly? So for a point was, it is m into r cross v, not v cross r. Who is it? Sarvesh. Okay. And for other planar objects, we'll come to that. Planar object, not necessarily planar, it is 3D objects. We'll come to that. Hold on, Sarvesh. But for point objects, it is m into r cross v, not v cross r cross v. Okay, clear, everyone? Now, I will change the question a little bit, guys. I'll change the question a little bit for all of you. And instead of, okay, this was the answer. Okay, instead of, oops, instead of highest point, what if I change the entire question? So sorry, I change the entire question to when it reaches the bottom. Imagine when it reaches the bottom, when it is back at its bottommost point. Just imagine that. So sorry. When it has again reached back its bottommost point, like means over here. So at this point, if I have to find the angular momentum, when it is at its ground level, ground level back. Okay, that is the question. So let's think, how do we solve? These options won't work. So I'm just erasing it just so that we extend the problem and figure it out. Okay, this is the question. When it is back to its ground level, then what will be the angular momentum about the same point? Interesting question. Instead of now the topmost point, instead of the topmost point. Now it is back at the ground level. So again, this u will be as it is, this theta will be as it is, it will be back over here. So when it lands back, the velocity will be the same. We all know it. So u will be the same, and u will be again making the same angle with this particular theta. Sorry, with this ground level. You will be making the same angle theta with the ground level, because this angle also has to be theta. It is a perfectly symmetrical shape which the path takes, of a projectile motion. So all these angles are theta by symmetry, nothing else. Now let's understand, to find angular momentum, we need the position vector. So this is my position vector, which is basically your r. This is that mass which is over here, which is having the momentum in this particular direction. Now think, in order to find angular momentum, should I use r perpendicular into p or r into p perpendicular? Which one do you suggest? Answer it in the chat box. Take a moment. If you're watching it, record it. Sir, can I still look for JEE second attempt like the April one, or can I join any other so I will work? Take the January attempt, the first attempt, as your mock test. Even in the last 1 month, 1.5 month, instead of getting 0, you can get at least 80 marks, no? Or at least 100 marks, no? You at least qualify, and getting 100 marks is not that difficult. Second attempt, then you prepare for 180 marks, 200 marks. Otherwise, you will have to prepare from 0 to 180, which is more difficult than 100 to 180. So give your January attempt at least for 100 marks, man. Okay? Yeah. Yes, very good, Sarvesh. R into P perpendicular. Why will I now extend this and drop a perpendicular, which is crazy to find? Instead, I will just take the perpendicular component of that velocity, which will be like this. Is that right? So instead of taking this, I'm just going to take this perpendicular component, which is going to be u sine theta, This is basically the perpendicular component of that momentum or velocity. Okay, so I'll be using r multiplied by p perpendicular. In this case, my r is also the range. And what is the range of a projectile motion? Try to recollect. 2u square sine theta cos theta whole thing divided by g. So instead of r, I will put the range, which is 2 times u square times sine theta times cos theta times divided by g. You can also write it as sine 2 theta if you want to, but I just put the basic formula. Then momentum wise, mass into velocity will be u sine of theta. Is that right? Let's condense it slightly. 2 will be there, m will be there. U square into u will be u cube. Sine cos sine, so it will become sine square theta cos theta, the whole thing divided by g. This is what I'll get as the answer instead of this one. So here it was mu cube sine square theta cos theta by 2g. Now 2 is there on the top, rest everything is the same. So it has now become 4 times. Can you see that? It has now become how many times? 4 times the angular momentum as compared to the top. It has become 4 times. Yeah. All right. I reply to all the genuine comments, Deepak Kumar, but still, while conducting the class, it is little bit difficult because, I want to maintain the flow of the class. Did you love the question? So same question, guys, has been solved in 2 different ways, but for 2 different things. Here I used r into p perpendicular because that was convenient. And at the topmost point, I used r perpendicular into p. It was convenient. So either formulas will work, but depends on which situation you have to use it. Okay, cool. So that was the idea behind teaching you these 2 things. Okay, we will do more questions now on angular momentum and how to find it out for point masses before going to rigid bodies. Okay, let's take up this particular question. Let's take up this particular question. The position vector is given, the angular momentum with respect to the origin at 2 seconds is how much? This was asked in JEE 2019 before COVID era, guys. Now, see guys, this is maybe your XYZ axis. There will be some, I don't know, some random position vector somewhere. This is your position vector. And maybe there will be some velocity vector. God knows which direction will it be in. I do not know. It's not given at all as of now. And you have to do R cross V to get the angular momentum. But how do I find velocity? Don't worry. Because position vector is given, I can find the velocity by differentiating it. See, this is my position vector. This is basically your position vector. In order to find its velocity, v bar, I'm just going to take dr vector by dt, derivative of position with respect to time. So 2t, so 2 will be outside, derivative of just t will be there with respect to I cap, minus 3 will be there, and just take the derivative with respect to time of t square, and this is in j cap direction. Just taking the derivative of our position vector over here, nothing else. Okay, so what will this become? Okay, is everybody clear? This is my position vector, guys. This t, 2t I cap, 2t I cap minus 3t square j cap was my position vector. I've just taken the derivative using the simple addition subtraction rules of derivatives, nothing else. I've taken two terms. 2 into 1, derivative of t is 1. This will be I cap minus 3 t square's derivative will be 2t. This will be j cap. So this is nothing but 2 I cap minus 60 j cap. Minus 60 j cap. See if this is fine. 2 I cap minus 60 j cap. Now if I try to find the angular momentum, I need to do r cross v. So I'll just do r into v now. R into v. R multiplied by v I will do. R multiplied by v I will do. Observe this carefully. My r vector is basically 2t I cap minus 3t square j cap. Okay, 3t square j cap. And if you see velocity vector, that is 2 I cap minus 60 j cap. Okay, now I'll do one thing. I'll substitute the value of time. I'll substitute the value of time over here. I'll substitute the value of time over here as 2 seconds. So see what do I get? 2 into t, 2 into 2 is 4. So it will become 4 I cap minus 2 square is 4, 4 3s are 12, 12 j cap. Just check this out. Multiply it with, this is simply 2 I cap. 2 into 6 is 12. So 12 j cap. Is that right? Now I cap will not multiply with I cap, j cap will not multiply with j cap. So what I will get over here, 4 I cap will multiply with minus 12 j cap over here, plus here you will have minus 12 j cap multiplying with 2 I cap over here. So 4 into 12 is 48, so minus 48, and this will be k cap, and 12 2s are 24, but with minus and minus it will become plus, so 24 k cap over here. So minus 48 plus 24 will, is that right? 4 12s are 48, 12 2s are 24. Yes, minus 48 plus 24 should make it minus 24 times of k cap. Now, once we got r cross v, we just have to figure out angular momentum. Angular momentum is mass into r cross v. Mass into r cross v. Where is the mass? Mass is 2. R cross v, we just got it as minus 24 times of k cap. So this will be minus 48 times of k cap. Minus 48 times of k cap is second option. Let's check it out. Yes, it is absolutely fine. Correct one. So r cross v will be minus 24. Finally, we have to multiply it with m also to get the angular momentum. Okay. Cool, perfect. Let's go ahead. Next question coming up on your screen, and here it is. A particle of mass 20 grams, a particle of mass 20 grams is basically released with some velocity along this particular curve as shown. The point A is at some height. The particle slides along that surface. When the particle reaches the point B, what is the angular momentum about point O? That is the question. What is the angular momentum about the point? When this point reaches over here, that mass will have some velocity, and this velocity is already perpendicular to the position vector with respect to this particular point O. This is our position vector. So to find the angular momentum, you need r value and velocity value, and you are sorted. R value will be this plus this. So r will be 10 plus 10, which is basically 20 meters. Only problem is for velocity. So it is clearly mentioned it is already released with some velocity. When it reaches here, it will have some new velocity which will be more. We can find using conservation of energy. So using conservation of energy principle, so initial kinetic energy plus initial potential energy will be my final kinetic energy and final potential energy. Initially kinetic energy will be half into mass into initial velocity is 5. Potential energy will be mass into g, which is basically 10, and height is also 10. Final kinetic energy is half into mass into v square. Final potential energy over here, we'll take it as 0, taking this as reference. M will cancel out. 5 square is 25, so this will become 25 by 2. 10 into 10 is 100, is equal to v square by 2 multiplied by 2. So 25 plus 200 is v square. So v square is 225. Therefore, velocity is square root of this, which is nothing but 15 meters per second. Now let's figure out angular momentum. Angular momentum is r into v into sine theta, r into mv into sine theta. So r is nothing but 20. Mass, how much is it? 20 grams. So 20 multiplied by 10 to the power minus 3. Velocity is 15. Sine theta means sine of 90, because angle is 90 between them. 20 into 20, it is 400 multiplied by 10 to the power minus 3 multiplied by 15. 15 fours are 60. So 60 will be there, and you will have more two zeros and 10 to the power minus 3. So this will become basically just the number 6, which is the first option, So this is how you can solve this question. Okay, fair enough, simple. All right, great. So these are the kind of questions which you can solve for point-based masses. For angular momentum of a point mass, whenever it comes, either you use this, or you can directly use the cross product, one of these things. Now, what to do when it is a rigid body? When it is a big body, then how do you figure out the angular momentum? So for that, let's take a rigid body. Let's take a rigid body, and it is being rotated about some axis. It really doesn't matter where that axis is, but some axis. And it is being rotated about that particular axis like this. This is the angular velocity. This is that rigid body, okay, which is being rotated. Now, this rigid body will be made up of many masses. Many masses. Let's say I take one mass over here, okay, and that particular mass will have some velocity. Let's say v1. That mass could be m1, and that mass is, let's say, at a distance of, this is the perpendicular distance, okay, perpendicular distance from the axis, at a perpendicular distance of r1. Similarly, some other mass here will have some other velocity, another mass will have other velocity, another mass will have another velocity. Like that, n number of masses will be there. And if you keep measuring the distance from the axis, r1, r2, r3, like that, so this will reach to rn. This will be the nth mass, so mn, and that nth mass will have some nth velocity, which will be vn. Each mass will have different velocities, but they will have same angular velocities. That is very, very important. So in general, I can say V1, V2, like that till Vn. All the masses have different velocities, but their omegas will be the same. The difference is R1, R2, R3, Rn. So that is why farther the mass, bigger circle, so more velocity, closer the mass, smaller velocity. So if it is going in smaller circles, less velocity, big circles, more velocity, even big, even more velocity. So that's why linear velocities are different, angular velocities are obviously the same. This is important now to find the angular momentum of that body, which is nothing but angular momentum of the first particle plus angular momentum of the second particle, like that angular momentum of the nth particle. Now, what is the angular momentum of the first particle? It will be nothing but mass into r into v1, m1 or basically if you want to write it in the proper way, it will be r1 into m into m1 into v1 into basically sine of 90 degrees. Why sine 90? Because r and v are perpendicular. Radius and velocity will always be perpendicular. This is the first term. Similarly, you will have the second term, third term, and the last term will be nth radius into nth mass into nth velocity into sine of 90 degrees. This is how the sum is going to look like. Sine 90 is 1 everywhere. And do not forget, all these velocities v1, v2 are nothing but omega r1, omega r2, like that. So the last one will be rn, mn. Instead of vn, I'm just going to put omega into rn. To write it in a much better way, I'll write it as m1, r1 into r1 is r1 square. Rn into Rn is Rn square. So it will become Mn Rn square. From everywhere, omega is taken out common. What is this particular entity? What is this particular entity, my dear students? Quickly think and tell me whatever is there inside this particular brackets when I take out omega common. This is the definition of moment of inertia. So this is nothing but moment of inertia of that particular body. So this is how you find out the angular momentum of a rotating rigid body. It's I into omega. So just to be clear, if you have any rigid body and it is being rotated, whether inside axis, outside axis, really doesn't matter. It is being rotated with some angular velocity. Then the angular momentum vector is simply moment of inertia about the same axis into angular velocity. Now, if you notice, it is rotating in this way. So if you hold your fingers of your right hand, the thumb will go up like that. So in this situation, the angular momentum is directed upwards. Angular momentum vector is going to be directed upwards in this scenario. So that is how you find angular momentum of big rotating bodies. Very straightforward. Now, if you notice, this is very similar to the linear momentum formula. Linear momentum formula. On left hand side, you have momentum. On the right hand side, you have inertia and multiplied with velocity. Remember, linear momentum was mass into velocity, P is mv. Angular momentum is moment of inertia into angular velocity. That is the only difference over here. Only extra word which comes is angular velocity. Here this is moment of inertia, and this is nothing but angular momentum. So it's very similar looking formula. Okay. Now you can also relate linear momentum with energy. So angular momentum also can be related to rotational energy. And I'll tell you how. If angular momentum is moment of inertia into angular velocity, we also know that rotational energy is half, instead of mv square, it is half I omega square. Just multiply and divide by I. multiply and divide by I, you will get half I square omega square divided by I. So it will become half, you will have I omega common, whole square, whole thing divided by I. So what is this I omega? That is angular momentum. So it will be nothing but half L square divided by the moment of inertia. That will become your rotational kinetic energy. This similar formula was also there in momentum and kinetic energy. The linear kinetic energy is half square of momentum, p square by m. Do you remember that? Half p square by m was the formula. Instead of mass, it is I. Instead of very similar looking formula. So this is for rotational kinetic energy. Rotational kinetic, rotational kinetic energy and how it is related to the angular momentum. Half L square by I. Instead of half P square by M, it is half L square by I. So remember all these formulas, very, very similar. And this derivation is simple and also gives you an insight of, actually speaking, this formula has come from the fundamentals of taking every single point mass and adding their angular momentums, you are getting the total angular momentum. So fundamentally, it is just the sum of each of these angular momentums. That's all. Yes, Abhijit. Similar formula, similar things. Okay, cool. Let's do some questions based on that particular concept. Find the angular momentum of 3 kg disc with 4 meter radius and 10 radian per second speed. Find the angular momentum of this. All right, find the angular momentum of this. That's the question. Let's see if you can do this particular question, guys. Angular momentum of a disk is asked. Disk means moment of inertia is mr square by 2. And we all know angular momentum is I into omega. But for a disk, moment of inertia is mr square divided by 2. So you just have to substitute. Mass is 3 kilos. Radius is 4 meters. So 4 square. Whole thing divided by 2. Angular velocity was given to be 10. So what is this going to be? 4 square is 16. 16 by 2 is nothing but 8 multiplied by 10. 8 threes are 24. So 240 kg meter square per second. Kg meter square per second. That is the answer. Yeah, how many of you got it? Yeah. Sir, if angular momentum is 0, can rotational kinetic energy be non-zero? No, rotational kinetic energy has to be uh, uh, also 0. That is provided, if it is same axis and all of that. Yes, for a purely rotating body I'm talking about. So if it is a purely rotating body, if you're measuring the angular momentum is 0, then that same axis you will see there will be no kinetic energy. Okay. Yes. Unless you take a point mass and you deliberately take the axis on the line of velocity, then it will have no kinetic energy. Sorry, no angular momentum, but kinetic energy will still exist. If you take a point mass deliberately on the axis, or the axis deliberately on the point mass. Okay, but otherwise, all rigid bodies, if it has angular momentum, it should have rotational kinetic energy. Next question on your screen, and here it is. If the rotational kinetic energy of rotational kinetic energy of a body with 4 kg meter square moment of inertia is 200 joules, find its angular momentum. Find its angular momentum. That is the question. If there is a body with some moment of inertia and some rotational energy, find what its angular momentum will be. Now, just some time back, I showed you one formula which related rotational energy with angular momentum. So maybe we might need it because the rotational energy is involved. And if I write down that formula, it says rotational energy is half L square divided by I. And we want to find L. So L square will be 2 times I times of K. So therefore, L will be root of 2 times I times of K. And I think I is also given and K is also given. That makes my job easier. So therefore, the angular momentum will be root of 2 is there, moment of inertia is 4 and rotational energy is 200. So this will become 4 multiplied by 200 into 2 is 400. 4 is a perfect square, so square root is 2. 400 perfect square is 20. So this will become just nothing but 40 kg meter square per second. So that's how we figure out the angular momentum using this formula. That is the application of it. Okay, so these kind of questions, very straightforward questions, also do come in the JEE Mains examination, and you should be aware of using these formulas at least few times. If you use it now, it will be there in your head, or else it will unnecessarily take extra 20 seconds, 30 seconds in the examination hall. Okay, so let's do one more question on your screen, and here it is. Yeah, here it is. 4 point masses, each of M, are fixed at the corners of a square of side L. The square is rotating with an angular frequency of omega about an axis passing through one of the corners, okay, of the square and parallel to its diagonal. The angular momentum is how much? This was a JEE 2022 question. Interesting. Now, the idea is, if you want to find moment of inertia, if you want to find angular momentum, you will need moment of inertia because it is I into omega, and I think omega is given. So you just have to find I and your job is done. So treat this like a simplified problem where you have to find moment of inertia, out of which one of the mass is on the axis and only 3 other masses are away from the axis. So these distances will matter. This is R, and this is R, because that is your R1, R2, R3, like that. This point mass will not have moment of inertia, will not have moment of inertia because it is on the axis. It is on the axis, so it does not have any kind of moment of inertia. So the only 3 masses which have moment of inertia are this, this, and this. Is that clear? Because this entire geometry, guys, is spinning about this particular axis. You can see that. Okay. Now, as it spins with this angular velocity, how much is this, this, and this? Out of that, these two will be the same. So to find that out, I know I can find the diagonal length. This is diagonal. This is basically the diagonal length. And the diagonal of a square is root 2 times of the side. And the side length, is it mentioned? Corners of a square of side length L. So it will be nothing but L times of root 2. So if this is L root 2, how much will this be? This will be basically the diagonal divided by 2. So therefore, it will be L root 2 divided by 2, which is basically L by root. This and this will be the same. So this will be also L divided by root 2. So this is L by root 2, this is L by root 2, this is L root 2. So we can figure out the moment of inertia. First mass has no contribution, so 0, plus m into L square, mass into L by root 2 whole square, plus m into L by root 2 whole square. Second mass also done. This is the third mass now. So m into L root 2 whole square. Summation of mr square. That's all. So this will be nothing but m L square by 2 plus m L square by 2 plus this will be m L square but 2 times. So half plus half is 1, 1 plus 2 is 3. So this will become 3m L square. Now we can figure out how much is the angular momentum because it is I multiplied by omega. I is 3ml square and omega is omega only. So 3ml square omega, that is our first option. That is our first option. That is absolutely correct. So sometimes a big question might be asked, but you have to solve it in steps. And one of the steps was finding moment of inertia. And to find moment of inertia, geometry was required. Without that geometrical understanding, you cannot proceed with the question. Yeah. All right. Perfect. Amazing. Amazing. Shall we move ahead, guys? Shall we move ahead to the next amazing question on your screen? And here it comes. If L and P are the angular momentum and linear momentum of a particle of mass m having position vector of r given by this formula, the force is in which direction? Direction of r, L, P or L cross P? This was a time consuming question in your JEE examination, especially this year only it came. So if you're lucky in the first go you get it, it's good. Else you will have to waste your time figuring out which options are correct. Now, this is basically A cos omega t I cap, J sin omega t A cap. I'll tell you what, if you do it by the traditional method where you from R you find velocity by doing dr by dt, then from velocity, let's say you find momentum because momentum is m into velocity. Then you can also find angular momentum because it is r cross p. Then you can also find force because from velocity you can also find acceleration, right? Acceleration is dv by dt, that will give you acceleration. From that you can get force, which is mass multiplied by acceleration. Look at the length of the question. For every single quantity you have to find derivatives, multiply with something, create cross product. It's a very lengthy question if you do it like this. This is something which you should avoid. That is what I'm trying to tell. This is something I feel, okay, this is definitely lengthy to solve, to check if the directions are same or not. Rather, use some visualization. I would say, rather, use some visualization. This is a very common equation, guys. This is very common equation. R is something cos omega t I cap, something sin omega t j cap. It's nothing but the particle is actually going in a circular path. The particle is actually going in a uniform circular motion. Basically, it is just that. And you are taking our position vector. This is nothing but your position vector like this. This is your position vector like this. And the particle is going in circular path. That means the velocity will be perpendicular to it along the circular motion in this particular manner. And omega is going to be constant. It is basically a uniform circular motion. Basically, it is nothing but a uniform circular motion. It's exactly that, nothing else. So this A cos omega t I cap is in x direction. A sin omega t is in y direction. That's it. That is the components of that position vector. Nothing great. Is that clear? Is that clear? How many of you realized it is basically a uniform circular motion? And in uniform circular motion, the force which exists is only centripetal force. So the force will be in this direction. There is no tangential force. And in the direction of velocity only, you will have linear momentum. You will also have linear momentum. And the angular momentum will obviously be like this. The angular momentum will be perpendicular to all of them. So the question is the direction of the force. The direction of the force, guys, that's what they have asked. Instead of doing all these nonsense, okay, direction of the Force is us. So you don't have to do all this nonsense now. Just quickly think and tell me. Just quickly think and tell me. Is opposite to the direction of R? The direction of the force is opposite to the direction of R? Is opposite to the direction of L? Is opposite to the direction of P? Opposite to the direction of L cross P? Oh my God, it's so simple now. Force and R are opposite of each other. Isn't it so obvious now? Isn't it so obvious now? How many of you wrote option A? Hi Pritija, good evening. I'm very good. I am feeling well. I was never at an issue. Yeah, but I've mentioned in before. Yeah, my issue, why I was not there last 1 week. Great, guys. Great. Now let's move to the next concept where the body might be rotating also and translating also. And then how do you find out angular momentum? In such cases, when the body is rotating also and translating also, for example, imagine there is some body over here. It is rotating also and it is translating also. And you have to find the angular momentum about this particular point or basically axis. This is translating and this is also rotating. You break it down into two parts. What you do is you still take that particular point and see where the center of mass of the body is. Show a position vector towards the center of mass. I will call it position vector of the center of mass. And see what is the velocity of the center of mass at that moment. VCOM. That is the first thing. Additionally, you sit on the center of mass of that entire body. You sit on the center of mass of that entire body, which is there. Second, you sit on the center of mass of that entire body, which is there, and then think as if it is spinning about the center of mass, and think as if it is just spinning about that particular center of mass with some angular velocity. And about the center of mass, it will also have some moment of inertia, ICOM. ICOM is the moment of inertia about the center of mass. So the angular momentum of any particular body which is rotating and translating is angular momentum of the center of mass, which is a point mass, plus angular momentum with respect to center of mass, where you have to use the rigid body formula, meaning the total angular momentum of that particular body will be, for the center of mass, which formula will you use, guys? It is RCOM cross M into VCOM, because it is a point mass, plus with respect to center of mass, it is spinning. It's a big body which is spinning. So I will use I omega formula. So ICOM into omega. So this is the formula for it. This is taking care of the translation of center of mass. This is taking care of the spinning with respect to center of mass. So this is the formula. So any body which is rotating plus translating, take the center of mass, take it like a point mass, and sit on the center of mass and see the entire body. Add those two angular momentums, you will get the answer. As straightforward as that. For example, imagine we had a rod like this. Which is having some mass, which is having some length, and which is spinning like this with some angular velocity. And the point over here is moving like this with some linear velocity u. And we have to figure out what is the angular momentum about this point. What is the angular momentum about this point, which is in line with the lower end of the rod at this instant? That is what we have to figure out. Example, this one. So what I will do first, I'll split it up into two parts. That's what I told you, right? What are those two parts? First, look at the center of mass of the entire rod. Center of mass of the entire rod will be over here, exactly in the middle. And that center of mass itself is moving with velocity u only. That will be that point mass. And it will be at how much distance from our axis, guys? That is very, very important. Our point is over here. Okay, this is L by 2. I feel we should take the line of velocity. Then this will become the perpendicular distance. Can you see? This will basically become R perpendicular. So the angular momentum of that particular point mass will be, if you use R perpendicular into momentum, R perpendicular will be L by 2. Momentum, how much will it be? M into U. And which direction it is going? It is going clockwise about this point. The velocity is like this. The point is here. So it is going in the clockwise direction. This is in the clockwise direction. If you take the point mass as it is. If you take the entire rod and sit over it, and now you are sitting on the center of mass and seeing it spin, which direction is it spinning? Like this. Then the angular momentum will be, if you use I omega formula, moment of inertia is ml square by 12, omega is omega, but this is anti-clockwise direction. So bear in mind, one is clockwise, one is anti-clockwise. So when you find the total angular momentum of that particular rod, one will be positive, one will be negative. You can take any one as positive and negative. So L by 2 into mu minus ml square omega by 12. That is the answer. Why is it minus? Because the directions. So directions also matter. Remember, this equation which I showed you is a vector equation. So obviously plus minus signs will matter. Is this clear? So take the center of mass of the body and find the regular way how you find the point mass's momentum. Then sit on the center of mass and then also find the angular momentum. Just have to add them. Okay. All right. Now, a similar question was also asked in JEE 2022. A spherical shell of mass 1 kilos is rolling as shown, and the magnitude of the angular momentum about the origin is this. So find that constant. Now, this particular problem, again, you have to break it down into two parts, guys. So, the point about which I want to measure the angular momentum is over here. You take the entire sphere as a point mass. The point mass will be over here. This is the center of mass. And that center of mass will be moving with some velocity like this, which is v. And because it is pure rolling, it will be omega into r. Only because it is rolling, v will be equal to omega r. Else it is not equal to omega. Now, technically, yes, this is my position vector, but I don't have to do that. If I take this as my line of velocity, then you will immediately see, instead of taking this as my position vector, I'm just going to drop a perpendicular over here, and this r perpendicular is what will matter to me for measuring the angular momentum. And needless to say that since this is a spherical body, this perpendicular distance is itself the radius of that spherical body. So when I use r perpendicular into p, r perpendicular is the radius, p is the momentum, which is m into v, but that velocity is omega into r, and that will be in the clockwise direction as it is. So it is going to be in the clockwise direction. That is the first part. Then next step, what did I mention? You take the entire body, you take that entire body and sit on its center of mass and let it spin. Then the angular momentum will be I into omega. This will be clockwise. Moment of inertia, what is it? Spherical shell, right? So it will be 2/3 mr square, 2/3 mr square multiplied by omega. I is this, omega is this. Very simple. Directions are same. So I feel we should just add them to get my total angular momentum. So this is m omega square r. This is 2 by 3. 3 plus 2 is 5. So this will become 5 by 3 m omega r square. M omega r square, 2 by 3 m omega r square. So 5 by 3 m omega r square. So if you see what is that number a over here, that will be obviously the number 5 as it is. Is that clear? That will be the number 5 over here. Is this absolutely clear? That will be the number 5 over here. Yeah. Vanakkam, Aniruddha. Yesterday I watched my 4-hour midnight session for the system of particles. My tomorrow exam very useful. I am so glad. Saktivel, it was very useful. Very good. Darshanil, I'm getting 180, 185 marks. Previous year paper, can I get 99 percentile? You are still on the borderline, because if you are getting that many marks and this year the competition is more, and considering at home the situation is different, she should always target at least 20 marks or 10 marks higher than the last year's cutoffs, or that too in the easiest shift. So in the easiest shift, it went to 200 marks. So you should target 210, 220 marks. Then you can be sure that, yes, I will most likely get 99 percentile. But almost there, you just have to push. You have 1 month, you can easily push. Yeah. Yes, very good. 5 is the answer right over here. This number A will be 5. Very good. Now let's go to the next concept. We have done and finding angular momentum. Everybody knows now, confident about finding angular momentum. Any point mass, big mass, rotating mass, translating mass, anything, you should be able to find the angular momentum. Find its direction, compare it with anything. Now, let's see how is angular momentum related to the torque. How is angular momentum related to the torque? If you take any angular momentum of any particle, it is nothing but r cross mass into velocity. Now I'll do one thing. I will say, let's differentiate. Okay, let's just basically differentiate and see what do we really get. So I just have to put d by dt over here, and also I have to put d by dt over here on both the sides. That's all. Differentiate on both the sides. As you can see, left hand side to straightforward dl by dt, but right hand side it's two things. But again, our r is usually constant, but sometimes it might not be constant, whatever. So let's use our product rule, uv rule. R cross m into dv by dt plus mv cross dr by dt. dr by dt. Okay. I'm taking the worst case scenario. Maybe r is changing. Who cares? So what will happen? Now, what is this? R cross m dv bar by dt is nothing but acceleration plus mv cross dr by dt is nothing but velocity. Now, this is the interesting part over here. If you take a vector, cross it with itself, a cross a, I cross I, j cross j, it's always going to be 0. So this is always going to be a big fat 0. So this will not come only. So I just will be left with, therefore, dl vector by my dt is simply put r cross mass into acceleration. But what is mass into acceleration? It is nothing but force. What is r cross f? That is nothing but your torque. That is nothing but your torque. So therefore, I get dl by dt is nothing but torque. I get dl by dt is nothing but my torque, and that is the derivation for relation between torque and angular momentum. Isn't it amazing? We just differentiated it. and we use some rules of cross product, and we use some basic definitions in mechanics, like dv by dt is acceleration, mass into acceleration is force, and r cross f is the definition of torque. So finally, I can then say that my torque is nothing but dl by dt. About the same axis, you cannot choose a different axis for torque and angular momentum. Like you measure torque about some random axis, angular momentum about some other axis. No, that will not work. This is very important. About the same axis, both about same axis, and in words, we can say the net torque on a body is the rate of is the rate of change of angular momentum, is the rate of change of angular momentum, which also means if I take a graph of, let's say, angular momentum versus time, and this is how the graph is. If you draw a tangent to that particular graph at any given point, doesn't matter where, you draw a tangent to that graph at any given point, that tangent which is drawn, it will be making an angle with our horizontal time axis, let's say theta. Then the slope of angular momentum versus time graph, which is also nothing but tan of theta, will be nothing but my torque. Very, very critical. So the torque will also be the slope of the angular momentum versus the time graph. Very straightforward. Is that clear, everyone? All right. Let's say it is mentioned to me if the angular momentum is L is equal to 2t square minus, let's say, I don't know, 9 j cap kg meter square per second. Find, number one, initial L and torque. The L when torque is 0. These are the two questions. Find the L when torque is 0. These are the two questions. The moment angular momentum is given and torque is asked, you just have to take simple derivatives, because that's what it is. Torque is rate of change of angular momentum. So what we do is start off with that. To find the torque is nothing but dl by dt. So it will be d by dt of our 2t square minus 9. So basically, oh sorry, there was 9t over here, right? Minus 90. Okay. So this will be nothing but a derivative of 2 multiplied by t squares. T square's derivative is 2t minus 9t's derivative will be 9 into 1. So therefore it will be nothing but 4t minus 9 is nothing but our torque. 4t minus 9 is nothing but our torque. Let's start the first one. Initial angular momentum and torque. So initial angular momentum, just put time as 0. So 2 multiplied by 0 square minus 0 basically 9 into 0 j cap. So therefore it will just be 0. So it is nothing but null vector. It is not there. It's not there only any angular momentum initially. If you ask me the torque value, we can figure that out also. Torque 0. Put time as 0. So 4 multiplied by 0 minus 9. Yeah. Everything will have that j cap. So this will just become minus 9 in magnitude, but in vector form, this will be just minus 9 j cap, and that will be Newton meter. That also is done. That also is done. Okay. So that is the initial torque and initial angular moment. Now the angular momentum when the torque is 0. So for the torque to be 0, this 4t minus 9 will be 0. So therefore, t will be 9 divided by 4. Time will be 9 divided by 4, my dear students. Use this time in angular momentum. So the angular momentum will be 2 multiplied by t square. That means 9 by 4 whole square minus 9 multiplied by time. Time is nothing but 9 by 4. And this is j cap. That's it. So angular momentum will be 9 square is 81. So 81 divided by 4 square is 16. 2 will cancel. So it will become 8 minus 81 divided by 4 j cap. So this will become, if you make it 8 times, that means you have to multiply by 2. So 81 minus 81 multiplied by 2 divided by 8 j cap. So this will become minus 81 by 8 j cap. That is the angular momentum when the torque is 0. Yeah. Hi Arju, welcome. Thank you for all the love from Kerala. Yeah. Okay. Below 18 years, I don't think so. Below 18 years, we don't hire uh, people because we want students to be at least 18 years of age. Yeah, because those are rules, if I'm not wrong. You cannot employ, no? Or else it will be child labor. See, child labor happens in your school. Miss will tell, go get the books from that staff room and come, go clean that bench, go write on that board, decorate, write a nice. That is happening in your school. Okay, not over here. Okay, cool. So we found the relation between torque and angular momentum. Okay, this was the relation. Shall we now go to the last concept, my dear students? Ready for it? I missed the number 2. Where? Why did I miss the number 2? Here. No, 4 square was 16. 2 and 16 cancels, becomes 8. 9 nines are 81 by 4. So when I take LCM, 81 will multiply 2 times. So 81 minus 81, 0 minus 81 will come and divided by 8. Is that fine? Check it out, Balakrishna Swami. Yeah. All right. Okay. Now let's do conservation of angular momentum. Now imagine there is some body or bodies or whatever, and there is some random axis. Maybe there are some forces acting on that body. There are some forces acting on that body. So about this particular axis, this body might be rotating. Maybe it has some kind of angular momentum. There is some kind of angular momentum, and these are basically some forces acting on it. Now imagine a situation where the torque by all these forces, the net torque by all these forces, R1 cross F1, R2 cross F2, Rn cross Fn, right? Imagine it to be 0. Forces are there, torques are there, but the torques are cancelling. Basically, all the net torque is 0. Net torque is 0. That is all the torques due to all external forces, they end up cancelling each other. They are all the torques due to all the forces cancel each other out. Cancel each other. So the net external torque, actually, the net external torque is 0. So when this happens, net external torque is 0. Then one funny thing will happen. Because torque is 0, what will happen is dl by dt will be 0. That means if a derivative of a number is 0, so the angular momentum must be constant. Angular momentum must be constant. That means, that is, the angular momentum is conserved. It maintains it. Angular momentum is conserved. Very, very important line. This is the principle of conservation of angular momentum. So if there is a body which is rotating and there is no net torque, it continues its angular momentum. I am not saying angular velocity. There is a difference. I'm saying angular momentum will be conserved. Velocity may increase, decrease. That is what you will see now. That is the weird part. Okay, velocity might change, but momentum angular wise will be conserved. Another weird thing is energy need not be conserved. So it might lose energy, it might gain energy. That is another funny part, because mechanical energy is only conserved if non-conservative forces are absent and they are not doing work. So there is no guarantee mechanical energy will be conserved. So very important line I will mention over here. Mechanical energy may or may not be conserved. There is no guarantee. May not be conserved. Very, very important. All these lines. So put it inside your head. When net torque externally is 0, then the total angular momentum is conserved. But mechanical energy, there is no guarantee. Linear velocity, angular velocity, there is no guarantee. Only angular momentum is conserved. Let me give you many examples of this. Now, you can try it out on a merry-go-round also. Yeah. Imagine this. This is a merry-go-round. And our Pandu is there. Our Pandu is there. And he's stretching his hands and is holding H.C. Verma book and I don't know, P. Bahadur. Two books he's holding. H.C. Verma, P. Bahadur, whatever. Halliday Resnick. Irodo is a very small book, so not Irodo. Irodo, very small book, right? Big books he's holding. IIT books. And that Pandu is spinning with some angular velocity. Let's say omega 1. Now, Pandu feels like, okay, as I am rotating on this merry-go-round, let me start reading it. He's rotating slowly only. Aram se is rotating like this. He feels like, okay, I should read these books. P. Bahadur, H.C. Verma. What do you think will happen to Pandu? Let's analyze this. Pandu decides, okay, I'm going to read this book and this book. What do you think will happen? He's brought it closer. In this situation, I don't feel the angular velocity will remain the same, because what happens is when you hold the books close to each other, then the masses are closer to the axis, which means the moment of inertia reduces. Moment of inertia reduces. Very important. Mr square. R is less, Mr square will be less. And what did I talk about angular momentum? Well, there is no torque. Nobody is pushing, pulling, rotating him from outside. External torque is zero. There is nobody pulling, pushing, rotating him. He is already rotating. So therefore, angular momentum, which is I into omega, must be constant. Must be constant. So think now, if moment of inertia reduces, what should happen to angular velocity to keep the product constant? That is why you will see angular velocity will increase. Angular velocity increases. Angular velocity increases. That is why omega 2 will be more than omega 1. So when he was holding it far away, he will be rotating very slowly, large moment of inertia. But angular momentum has to be conserved. So as soon as he brings it close, moment of inertia reduces. So angular velocity has to increase. As soon as he again takes it back, again the angular speed will reduce. Because I into omega has to be constant. Again brings it close, again it increases. So that is the dynamics. It's very funny. You try it out in a park or in your playground, you will see it. Okay. I'm so glad, Arju, you love it. And you're so much enjoying it. Okay. Perfect. Not just this, there are many more examples of conservation of angular momentum. Okay, there are many more examples of angular momentum conservation, like our sun. Yeah, our sun right now is huge. And I don't know how many of you know this, but even our sun is spinning. Just like our earth is rotating, even our sun is spinning with some angular velocity right now. And a lot of solar flares are there, like this, right? Solar flares. So many things will be coming out from the sun, dark spots, so many things are there. This is our sun. But our sun will die after many years. Yeah, our sun is going 5 billion years, 10 billion years, like that. A lot of billion years are going to be required for the sun to lose its fuel, to lose its energy, and eventually the sun becomes something called as a dark thing, which is a white dwarf. It's very dark, but it's still called as a white dwarf. Okay. So that is going to eventually turn into white dwarf after many billions of years, after losing the nuclear reaction, nuclear fuel. It's no longer going to create solar flares. It is just going to be a chunk of mass. Right now, because of that explosions, there are, like in Hiroshima, Nagasaki, there were two nuclear explosions. Imagine millions of nuclear explosions are happening on the sun every second. Yes, every second, so many lakhs of explosions are happening every second. So much fuel is there, it's very huge. Okay, so what happens? All the mass is being pushed everywhere outside. So a lot of pressure is there outwards. Inwards pressure is there due to gravitational pull. So gravity will try to condense the mass, but the nuclear fuel will try to push that mass away and keep the sun huge. If that nuclear fuel goes out, then the explosions won't be exploding and pushing all the masses on the periphery. Only the gravitational pull will now condense it into a very small, dense object. So this is going to be small and dense after the nuclear fuel is over. So now when it starts spinning, my dear students, it will spin very fast. It's crazy. So a lot of people think, okay, if the sun is rotating like this, so after it dies, it's just going to die, it will be just there. No, it will be spinning so fast. It will be spinning so fast after billions of years. And sometimes what happens is, if there are some extra materials, compounds and elements, especially magnetic materials inside that particular star, then those magnetic materials, those charges, etc., they create current loops and they can create magnetic field around them, which is extremely strong. There were some neutron stars, which is like white dwarf only, but much smaller in size. So they basically end up rotating so fast, and if there are charges and magnetic materials around them, they end up creating crazy electromagnetic fields around them, and those electromagnetic fields are extremely strong. And a lot of other things happen because of those electromagnetic fields, like the Earth's minute magnetic field of barely 10 to the power negative 4 Tesla is enough to create Aurora boys and those northern lights and protect us like a shield from the solar flares. You can imagine magnetic field of 10 to the power 6 and 10 to the power 7 Teslas on a neutron star, what kind of effects it will have. It's going to be crazy. And when such neutron stars interact, they are like two huge magnets in the universe doing a dance, isn't it? It's going to be crazy. So that's the extent till which angular momentum plays a role. So from a small thing, just because it shrunk, because the nuclear fuel was lost, it starts spinning and the electromagnetic effects take place, and then it causes more and more effects, and there is a dance in the universe. Is that right? Yeah, perfect. Great. So there are many more examples like that on angular momentum conservation. Say, for example, this one. There were two disks given. This particular disk is having angular velocity omega, has moment of inertia I. This has a moment of inertia of 3I, and it is rotating like this with 2 omega. Chuma random example. They both touch each other. Right now they are not touching each other. This is this axis. They both now end up touching each other. They will rub against each other, and they will now move with one common velocity, because this is bigger, this has more velocity. So I think eventually they will end up moving like this. So question is, what is their final angular velocity once they are brought together and they rotate? So they are basically brought and rotate together as one single chunk. So question is, find that angular velocity. This kind of question is very common. Let's see how do we do this. First of all, in such questions, you will notice that whatever touching action is there, whatever friction is there, it is internal. There is no such external force. So during that touch and rubbing, those are all basically internal forces. Those are all basically internal forces. So still our external torque, from outside you have not given any torque, so external torque is 0, and that is the reason why angular momentum must be a constant. Angular momentum must be a constant. Is that clear? Why angular momentum is a constant? From outside you are not doing anything. You just taken those two disks spinning and you have brought them together. They will rub, and eventually they will start rotating together. So in that process, the rubbing action, friction, touching, normal, those are internal forces. From outside, initially you had given that spin, that is over. Now they are spinning and now they touch. So they will rub and they will end up moving together with a new speed, common speed. So if you ask me what was the angular momentum before versus afterwards, originally this big disk will have angular momentum of 3I into 2 omega, and that is anti-clockwise. So this will have clockwise, that means it will be negative, and it will be just I into omega. I omega is the angular momentum. So for this one, it is 3I into 2 omega. For this one, it is I into omega, but opposite. So minus sign. Lastly, it is anti-clockwise, so I have to keep it positive. The final moment of inertia will be 3I plus I into final angular velocity. So this is 6 minus 1, which is 5 times of I omega, will be 4 times of I omega. I cancels. So therefore, my final angular velocity will be 5 by 4 times of omega. So this is the new common angular velocity. This kind of question is very, very common, let me tell you. Yeah. Arju, physics class? No, tomorrow you have chemistry class marathon. And then after that, you will have, what do you say? Physics class the day after that. Let's do this particular question. Very similar question, what I told you. But instead of I and 3I, omega and 2 omega, they have given I1, I2, and their velocities are omega 1, omega 2. That's the only difference. They are rotated coaxial and they are now brought in contact. They are rotating with same speeds and respectively, okay, and they are now brought together. The loss of energy is asked. This is a very interesting question because just now I told you during the discussion of angular momentum conservation that even if this is conserved, there is no guarantee mechanical energy is conserved. So a lot of people think there is no energy loss. That is wrong, absolutely. And that is what this problem will also prove in a way. So let's try and do this particular question. Okay. So in this question, again, same logic, guys. You have two disks, different, you have two different disks, two different moment of inertias. Finally, they are brought together and rotated about a common axis. They were earlier different and then they are brought together. That's it. That's the only thing. All right. So let's try and do this particular question. How do we do it? First of all, angular momentum is conserved. Angular momentum is conserved since net external torque is absent. So initial angular momentum will be I1 omega 1 plus I2 omega 2. Final will be I1 plus I2 both together into nu omega. So therefore, from this, I'll get omega is I1 omega 1 plus I2 omega 2 whole thing divided by I1 plus I2. That's what it is. Now, the question is not that. Question is figure out the loss of kinetic energy. So let's figure out how much was it there initially. So initial kinetic energy was half I1 omega 1 square plus half I2 omega 2 square. What is there finally? So Kf is half I1 plus I2 into omega square, which is half I1 plus I2 omega. Final omega is this one. So it will be I1 omega 1 plus I2 omega 2 whole thing divided by I1 plus I2 and this whole thing square. Correct? Omega is this quantity, right? So I have just got that quantity right over here and I've just squared it. So the moment I square it, what do I see? I1 plus I2 will get cancelled. So I'll be left with I1 omega 1 plus I2 omega 2 the whole square divided by 2 times of I1 plus I2. That's it. 2 times of I1 plus I2 because one of the I1 plus I2 will get cancelled on. Now we have to just subtract both of them. So let's do that subtraction bit and see how much are we really getting. Okay, let's try that out. How much are we getting the subtraction as? So question is finding out the loss of kinetic energy. It will be initial kinetic energy minus final kinetic energy. So how much is initial? Initial is this much. So it will be nothing but half I1 omega 1 square plus half I2 omega 2 square minus, minus this minus. Final kinetic energy is exactly that one. So let's substitute that. So it will be I1 omega 1 plus I2 omega 2 the whole thing square divided by 2 times of I1 plus I2. That's what it is. Just check this out. 2 times I1 plus I2. Now you just have to solve this, guys, and you will get the answer now. Okay. So as you can see, 2 is common. I1 plus I2 is not there. So make the denominator common first. That's the first step actually. So keep the common denominator. It's going to be a big expression. It's going to be a very big expression over here. So it will be 2 times of I1 plus I2 as common. So here we'll have I1 omega 1 square multiplied by I1 plus I2 plus I2 omega 2 square multiplied by again I1 plus I2. Okay, I1 plus I2, and then that minus sign is going to come, and then we will have this whole thing square. So I1 omega 1 plus I2 omega 2 and this whole thing square. Is that right, everybody over here till this particular point? If you notice, many terms will get cancelled also. Like for example, when I do I1 omega square into I1, it will become I1 square omega 1 square. If you notice, this is A plus B whole square. So first term will be I1 square omega 1 square. So that term will get cancelled. Many terms like that will be getting cancelled. Same thing here also. I2 omega 2 square into I2 will be I2 square omega 2 square, which will be getting cancelled over here also. Yeah. So many terms are there which will get cancelled like that. So you can do that math. So I1 square omega 1 square plus this is nothing but I1 I2 omega I1 I2 omega 1 plus here we will have again I1 I2, this is omega 1 square, sorry, I1 I2 omega 2 square plus I2 square omega 2 square minus, yeah, this will be all minus, many times minus is going to come. So first will be minus I1 square omega 1 square I2 square omega 2 square and 2 times I1 I2 omega 1 omega 2. So all these will be minus, and of course this big denominator, with your 2 times of I1 plus I2. Okay, so that's how you should proceed with it. Yes, it's a lengthy problem, but this was asked in JEE Mains. And you will see many terms, like for example, this one will get cancelled with this one, sorry, not this one. This one will get cancelled with this one. Yeah. Over here, you can take I1, I2 common, and this will be omega 1 square, omega 2 square, and see what are you getting. I1, I2 is basically common. You are getting omega 1 square plus omega 2 square minus 2 times omega 1 omega 2 whole thing divided by 2 times of I1 plus I2. What is this? A minus B whole square basically. So this will be nothing but I1, I2 and this will be omega 1 minus omega 2 the whole square, whole thing divided by 2 times of I1 plus I2. That's the final simplification. You cannot go simpler than that, I believe. So I1, I2 divided by 2 times of I1 plus I2 into omega 1 minus omega 2 whole square, which is basically our third option. Yeah, which is basically our third option. That is absolutely correct. So beautiful question. As you can see, we first saw this is very similar to our previous question, but everything is in variables. So that's why it becomes lengthy, but it is asked. So draw the diagram, conserve angular momentum, find initial and final energies, then do subtraction. After subtraction, it is pure algebra and concentration. If you miss any term, you will get a wrong answer. Okay, cool. Yeah, perfect. Let's go to another question coming up on your screen. Let's go to another question coming up on your screen. Are you loving these questions, guys? Are you loving these questions? Yes or no? Put up a heart emoji in the chat box. Let's do this question. Wow, it's such a brilliant question, guys, what I have just made over here. There is a rod which is hanging like this from a hinge. There is a small point mass which hits it with some speed at the end of the rod and gets attached to it. And now the rod with the point mass rotates. So when it just starts moving, what is that velocity of angular velocity? That is the question. Yeah. Is that clear? Yeah. Sir, will Vedantu hire me if I write what you want, sir? Pritija, if you are below 18, then no. Above 18, yes. Hmm. So let's see how do we solve it. Now, first thing, let me tell you what will work, what will not work. Immediately, you'll be like, sir, angular momentum conservation. I'll be like, why did you think of angular momentum conservation? Because the lecture says angular momentum. Let's say this question came in the exam. How do you know what is conserved and what is not conserved? Okay. So first of all, because it is clearly mentioned that the bullet sticks to the rod, what kind of collision is it? It is definitely inelastic collision. And in any kind of inelastic collision, obviously, what is not conserved? Mechanical energy. Mechanical energy is not conserved. So if you even thought about conserving energy, that the initial energy of the bullet is the total rotational energy, that is wrong. Mechanical energy is not conserved. So that is gone. I can't conserve energy. So then many people think, sir, let's conserve linear momentum. But there also, there is a problem. Imagine when this bullet hits that particular rod and that bullet is very close to that particular rod over here. So let me show that situation. In fact, so when that bullet is just touching that particular rod, okay, it is coming. So don't you think that the rod will suddenly try to get itself detached from the hinge point where it is pivoted? Just visualize it. This rod is just hanging, something comes and hits, you feel some force here, right? So don't you see that there will be a sudden kind of an impulse? So there will be an impulsive force on the rod, from the hinge, because this is colliding with the rod, colliding with that particular rod. And because there is an impulse, that means there is an external force. There is an external force on the rod plus that particular bullet. And whenever such an external force exists, my linear momentum is not conserved. Linear momentum, linear momentum is not conserved. Is not conserved. See if this is in your head. Why linear momentum is not conserved? Lot of people say, sir, M into V is total linear momentum of the rod plus the bullet system. Wrong. There is a external impulsive force. So you cannot do that. So now you might be wondering, sir, will even angular momentum be conserved? Because this is an external impulse. Absolutely right. External impulse is there. So maybe angular momentum is not conserved. Oh my God. Sir, external force is there and that too, it is huge. It's an impulsive force. So angular momentum is also not conserved. So that is a big headache. Then what should I do now? But then there is a small trick. And the trick is, if you go back to our derivation, and when I gave you this formula, I said torque is rate of change of angular momentum. So if you measure the angular momentum about the axis, the torque should be also about the same axis. You cannot have two different axes, which is obvious. So that means when I saw the conservation principle of angular momentum, when I said torque is zero, then the angular momentum is conserved about that axis where the torque is zero. What do I mean by that? There is a fine hidden print over here that maybe There could be certain axis about which the torque is not zero, because torque depends on the axis. If you change R, force might be the same, but R cross F will change if R changes. So possible that about different axes, maybe this or this and that, torque is not zero. So angular momentum is not conserved about those axes. But about one axis, the torque is zero. And that is where the angular momentum is conserved. And that is why this principle becomes very tricky, because so many axes could be possible. You need to be smart enough to figure out about which axis is the net torque zero, and that is where the angular momentum is conserved. Did you guys understand the crux of the problem? Yeah. So going back to this particular question over here, I realize that if I choose my axis as this axis itself, the hinge, so that is very interesting. About the hinge axis, about the hinge axis, the external torque about the hinge axis, the torque of that particular impulse will be zero. This is very, very interesting, because R is itself zero. Whatever is the force, even 100 Newton meter, 1000, 1 lakh Newton meter, doesn't matter, torque will be zero. So the net impulsive torque will be zero, and therefore angular momentum is conserved only about that hinge, only about the hinge axis. This is very, very super duper interesting, guys. That only if you take the hinge axis, it is definitely going to be conserved. But let's say I choose this axis, center of mass, this point, then it is not going to be conserved. Because about those points, the torque will be there. For example, somebody chooses this as the axis, center of mass. This impulsive force will create a torque, and the torque means no angular momentum conservation. Even if you choose this point, there is R over here, R cross F will create a torque. So angular momentum is again not conserved. So only the hinge point is there about which you can conserve it on that rod bullet system. How many of you got this concept? Why mechanical energy is not conserved? Why linear momentum is also not conserved? Because force is there. And angular momentum is only conserved about a special point, not all points. Usually it is very simple, but this is a tricky problem. So now let's figure out what is the moment of inertia before, what is the moment of inertia afterwards, and all of that. And then we can conserve it very easily. So if you ask me what is the moment of inertia of the system or before, this rod is at rest. This rod is at rest. So zero, I will put moment of inertia in different color maybe. So zero moment of inertia for the rod. And for this mass, it is at L distance. So it will be ml square. This is for the bullet. This is for the bullet. This is basically for the rod. But when both of them stick to each other and move as a combined mass, then it will be ml square for the bullet, m into L square for the bullet, plus for the rod, it will be mass, which is 3m, L square divided by 3. Remember, ml square by 3, when you have the rod which is pivoted at the end, at the center it is by 12, at the end it is by 3. So by 3. So that is why it is so. So this will become 3 cancels, so it will become 2ml square. So this is for the rod, this is for the bullet system. This number 3 is there because it is end pivoted, end pivot, not at the center. 3m is originally the mass of the rod. So now it is a straightforward theory. So conserving angular momentum, initial angular momentum is ml square multiplied by initial velocity. Finally, it is 2ml square into final velocity. What is omega? Omega will be, think about it, I mean for this particular bullet, that omega, yeah. So when you have this thing going like that at a distance of L, this omega will be U divided by L. because U will be omega L, omega will be U by L. So this will be U divided by L into ml square is equal to 2 ml square multiplied by omega finally. So ml square will cancel. So omega will be U divided by 2 times of L. So we have got the answer. Omega will be U divided by 2 times of L. Understood? Is that clear how we solved it? So it's a brilliant question what we just did over here. And you know how we have not used any of the other two principles, and conservation of angular momentum, that too valid about a special axis, not any other axis. So I've kept one homework question for all of you. So try to do this as homework. It's not difficult. I'll just give you a hint. So in this particular question, the angular momentum is measured about A, and then it is also measured about B. Same mass, it's like a conical pendulum. So conical pendulum, you remember, it goes like this. So first you are measuring about a point in the plane of the circle. Second is the topmost point, the apex of the cone. And these two angular momentums, you are figuring out whether they are changing or whether they are constant or changing direction. That's all. So for first mass, for first point, r vector will be like this. For the second point, the position vector will be like this. Both cases, velocity is along the horizontal plane only. So visualize it, you will easily be able to understand and mark the option. This was asked in 2021. Okay, so we have done these questions. Answer is there on the next slide. We did this also. Yes, perfect. And that's the end of today's class. And remember, the notes, everything, please do not forget to like the lecture. Okay, and smash the like button down there, mark your attendance, put up the comments with the homework answer, whatever you think. The PDF will be shared over here. You can see ask with any doubts. Click on this particular link, it will open up, and you will see bottom there are options like discussion, quiz, or doubts or something. Description, click on description. There you will find download PDF option. Description, if you click over here, you will find download PDF, quiz, doubts, anything you can ask. Timestamps will be generated after some time, everything. So Ved AI is helping you absolutely free of cost. Okay, so make sure you are doing that, right? Thank you. Thank you guys so much. I hope you enjoyed the class, and thank you for subscribing and thank you for liking. That's the end of rotation and rigid body. Bye bye. Take care.